Ngalakin kadijan nyunga boja.
Stuart. I'm trying to run Zoom here, right? So I'm running Zoom, but how can I share the screen?
It's here, screen.
Yeah,
So you just
yeah,
start. Do you want to share your voice also?
yeah.
Turn it on and start.
So where is
Maybe you'd better restart it.
Huh?
Restart the Zoom.
So
Do you need to close? No. Don't end session. Don't end session. I mean, just to close this.
what's that?
Just start. Yeah. For this side. Join.
No, I'm start. I need to start this meeting. That's where
But how you send this to the online student?
I've already sent the link. So that's
Yeah, use that link. No,
yeah.
use
That's
that link.
that's the link.
That's the link.
So I don't think it works, right? Doesn't work, right? Huh? It doesn't work.
Yeah. You normally just start broadcasting so you can.
It doesn't work. Are there
Are
any?
you the
Yeah, I'm the host. Yeah.
holding this session?
Let's start again. Right. So share screen.
Yeah, sure. Is this screen? Share content and
Screen, right?
yes, screen.
So yesterday I was able to start broadcast.
Yeah. Why
Yeah.
today it's not?
It's not. I think we don't bother.
Maybe you can try to use this. I think they also have some recording system.
Yeah. I'm using that. Yeah. Can you ask him to come? All right. Welcome all again. Today we begin our lectures for power system analysis. This lecture is recorded in Echo 360. So if you are unable to join us live, face to face, you can watch this on Echo 360. Now we've been trying to actually live stream this lecture as well. I'm having difficulty. I think on the other side, those of you who are joining us on Zoom, sorry, is he here? Okay, that's okay. For those who are joining us on Zoom, you perhaps can't see the screen, but I'm just going through the lecture slides. You have the lecture slides. You can hear me, so you can just follow it by scrolling through the lecture slides, because as I speak, you will know which slide I'm referring to. So that's the best we can do for today in terms of live streaming. I tried this on Monday as well with Teams. It didn't quite work because trying to do face-to-face, record Echo 360 and also live stream is difficult. But we'll try and resolve it for future, but at least you have the recording. So the first lecture is introduction and review. And if you want to do further reading on this particular chapter, you can read this textbook on power system analysis and design by Duncan, Glover, Sharma, and Thomas over by. So if you want to do some further reading, that can be done. I guess this book is available in the library. So if you want, it's online as well. So you can read. It will be the relevant chapters are chapters 1 and 2. So what is the table of contents for this particular chapter? So we'll just talk about the power system in Western Australia, right? Give you an understanding of the power system, the Southwest interconnected system and the Northwest interconnected system. What's going on in the electricity system in Australia, we'll discuss that. We'll discuss the vision for future electric grid, what the electric grid is going to look like in the future, because we know there are a lot of changes, interesting times for power engineers. The electric grid is changing from what it was, some time ago. It was originally built about 100 years ago, and it remained pretty much the same up until now, and we are undergoing lots of changes, so we'll talk about that. Then we will just review some electrical fundamentals which you already know. Phasor representation of electrical signals, we'll review complex power, and then we'll talk about balanced three-phase circuits. So you have learned this before, but we will review those in this first lecture. And also I must say that I was meant to take the whole of 12 weeks of lectures for this. Now unfortunately, due to a family emergency, I have to fly interstate, so I will be away for 1 week. And when I come back, I will have to self-quarantine myself for 2 weeks. So during that period, Lu Jin will take over. It's just an unfortunate thing. I have to go. But you can connect with me, and I will take over after that. Your education won't be interrupted. All right. So what's the power system in Western Australia look like? Well, in general, electrical power system has a few components. It needs to generate electricity. It needs to transfer that electricity over some transmission lines to an end user. So in an electrical network, the one in Western Australia and any electrical network for that matter, we can identify a generating plant. Somewhere we will generate electricity. It may be we are converting chemical energy in coal into electricity, or we are utilizing kinetic energy in a waterfall to convert it into electricity. Could be we are accessing solar power and converting that into electricity. So there has to be a generating plant, right? And then this electricity has to be transmitted over long distance. So there may be a transformer to step up the voltage. Because when you step up the voltage, if you wanting to transmit a certain amount of power, if you step up the voltage, power is V times the current, right? Or VI conjugate, V times current. So if you step up the voltage, the current's going to reduce for the amount of power that you want to transmit. And then the I squared R losses along the lines is going to be reduced. So it makes sense if we want to transmit power over long distance to then step up the voltage, transmit the electricity over some long distance utilizing transmission lines, and then and that we refer to as the transmission network, right? And then when the electricity reaches the residential areas where the electricity can be consumed, or in some commercial areas where there are industries, then this voltage can be stepped down, again using transformers. And then this section of the network where all the houses are connected, we call that the distribution network. So there's a transmission network which is high voltage, medium voltage, and then we'll use transformers to step down the voltage, and that section of the network is what we call the distribution network. So if you think about the electrical network, we have on one side we have the generators, we have the transmission and the distribution network, and then we have customers accessing power from this grid, electrical grid from all over the place. So traditionally, electrical system is a centralized system. Like you would generate electricity in some remote location, and you would transmit it, and customers on the in the distribution network in residential areas will consume power, and also industrial customers as well will consume power. But the situation is changing now, right? Because we are also generating electricity on the customer side. On customer, so they are not necessarily called customers now, they are prosumers. Consumers of electricity and producers of electricity. Prosumers. Because customers now, most of the customers have rooftop solar, so during daytime they generate lots of electricity for their own consumption, and in fact excess electricity, and if they don't have storage, then this electricity will be injected into the grid, and then essentially you're a generator, a small generator. So this is how the electrical network looks like, and this is a map of Western Australia, right? In this map of Western Australia, we see the green section. Green section extends up north to Geraldton, Kalbarri area, right? In the south to Augusta, Denmark, and Albany, and inland to Kalgoorlie and Coolgardie. So you can see the map here, colored in green. And Western Power is in charge of this section. And this section is called the Southwest Interconnected System. Southwest Interconnected System, right? Swiss. It's called Swiss. And in the Pilbara, so Western Power is in charge of this. We'll talk a little bit more about the Swiss. The rest of Western Australia, which is covered in orange, of course, the whole of Western Australia is not seen in this map, but you know the map. In the Pilbara region, there is also what we call the Northwest Interconnected System, serving those, mining sites, mining companies. And also, the other parts of Western Australia, we have isolated grids in separate towns. And Horizon Power is in charge of those sections, colored in orange. Only Western Power is in charge of the Swiss. Northwest Interconnected System and other isolated towns are managed by Horizon Power. Now, we need to talk a bit more about the Swiss, because three utilities provide services in the Swiss, not only Western Power. So what are the three utilities that provide services in the Swiss? We have Synergy, right? When you receive the electricity bill, you probably, it's a bill from Synergy. Because Synergy is a retailer, right? So we buy energy from Synergy. So if we are a residential customer, right, and a non-contestable customer, in other words, if our energy consumption per year is less than certain megawatt hours, I think 5 or 6, something you need to check. So as part of a little bit of homework that you need to do, just check up on contestable customers and non-contestable customers. So all the residential customers, I would say, residential customers are non-contestable customers, meaning that we have to buy energy from Synergy. We can't go through another retailer. We have to buy it from Synergy. So Synergy has a monopoly. We got to buy, right? So they are a retailer, but there are other retailers. So if your energy needs are, more than a certain amount, right? Energy, what is energy? Megawatt hours, right? Megawatts is power. Megawatts times time, megawatt hours or kilowatt hours is energy, right? Kilowatt hours is energy. But if you're talking about annual energy consumption, it makes sense to talk about megawatt hours, right? So if your energy consumption, like if you're a commercial customer and if your energy consumption is a lot higher than some set limit, then you're a contestable customer and you can choose your own retailer, right? You can buy energy from a retailer of your choice. So there are lots of retailers. Synergy is one of them, and that's the one all the residential customers need to buy energy. But Synergy also owns generators. They're not only selling electricity to customers, they also own generators, right? So if you remember that first map I showed, the generators, the transmission distribution network, and then the customers. So on one side, Synergy can sell energy to the customers because they're a retailer, and on the other side, they are a generator as well. They can generate their own electricity. But Synergy is not the only generator, but there are other generators. There are other companies that generate electricity and inject into the grid, right? So then what is Western Power? Western Power is in charge of managing the network, the transmission and the distribution network. So you could even say that Western Power is a poles and wires company. Poles and wires, because they manage the poles and wires, right? Electrical, but of course all the other gear that goes with it, like the transformers, the switch gear and all that, right? So they are a poles and wire company. They are in charge of the transmission and the distribution network. Then we have the Australian Energy Market Operator. So I said, we have generators on one side, we have consumers on the other side, right? And there are lots of generators and there are a lot of retailers that buy energy. So Australian Energy Market Operator manages that buying and selling of electricity. So it's like the stock market, you buy and sell shares. Some people sell shares, some people buy shares. So there's some people sell electricity, some people buy, right? Just like the stock market, a particular stock is a function of time. The value of a stock can be a function of time. It fluctuates, right? Fluctuates. Like that, the price of electricity can fluctuate, right? Price of electricity can fluctuate. It does fluctuate. So although we pay a fixed price for electricity, price of electricity fluctuates. It changes in time. Every 30 minutes, price of electricity can change. But we buy energy from the retailer, Synergy. We pay a fixed price throughout the day. This situation can change in the future. Right? Now, why does electricity price fluctuate during the day? What is the reason for that? Correct. Yeah, supply and demand, right? Just like anything else in the market. Supply and demand will determine the price. Okay, let's try and understand this more. So let's say the demand is less, right? Now to produce electricity, not all the generators will cost the same. Some generators, it will be cheaper to produce electricity using some generators it will be more expensive to generate electricity. Yeah. So if you generating electricity, for example, using coal, it might be cheaper. It's cheaper. So and coal power stations are not that easy to turn on and off. So coal is generally then used as to provide us the base load, which will operate constantly. It's cheap and you don't want to turn it on and off. You can't. It's expensive to do that. Then there are other types of generators like diesel generators, right? Which you can perhaps turn it on and off quickly, but more expensive to run, right? So the point I'm trying to make is some generators, it's cheaper to generate electricity using some generators. There are other generators which are more expensive to generate the same electricity. So depending on the demand, you might have to utilize the cheap ones as well as the expensive ones. But if the demand is low, then you can utilize the cheaper generators. So obviously, when you dispatch generators, dispatch energy, you would try to utilize the cheaper generators first, and then you bring on the expensive ones if you have to, because the supply and demand of electricity has to be matched, right? Energy is conserved. So what you consume has to be generated. Yeah. So we can then understand that price of electricity can fluctuate throughout the day, right? And that depends on supply and demand, and also due to varied costs of generating electricity using different generators. So it makes sense, right? So you now understand there are retailers, there are generators, right? Several generating companies, there are several retail companies, but we deal with Synergy as residential customers. And then there is an Australian energy market operator which facilitate that buying and selling of electricity, right? So what I encourage you to do, now I told you you can go and look up the definitions for contestable customer, non-contestable customer. You can also just check up some information on the internet on the Australian energy market operator, Western Power, right, and Synergy. Now, we know that these guys, these three utilities are responsible, provide services in the Swiss Southwest Interconnected System. Now, Horizon Power, on the other hand, is a vertically integrated company. So what does that mean? Vertically integrated company means they are in charge of everything. They generate, they maintain the poles and wires, the network. They also sell electricity to customers. So they do the whole service. So that's called vertically integrated. Some commerce term that is that's being used, right? So they are vertical. And Horizon Power also claims, now you must have heard a lot about microgrids in articles, papers, news, right? Horizon Power also claims they are experts or have a lot of expertise in the microgrid space. Why? Because they manage isolated towns. So what is a microgrid? Microgrid has generating sources, right? Has loads, has storage. So essentially, microgrid is like a mini grid, and has a well-defined electrical boundary, and a microgrid can connect or disconnect from a main grid and operate autonomously, independently, right? So it's like a section of a network, electrical network, that can disconnect itself and operate independently. So it can have its own generation, own storage, has its own loads, right? Can operate independently. So if you consider an isolated town, well, we could say that's an isolated microgrid. It can't connect to a network because there is no connection, but there could be a situation where there is a network, but this town will primarily be on its own, but when there is no sufficient generation, it will then connect and take energy from a main grid, yeah, the microgrid. So Horizon Power also claims that they have a special expertise in microgrids because of the their operation in Western Australia and the geographic nature, the vastness of Western Australia, and having to serve all these isolated towns. They claim capability in that space. All right, so what's going on in renewable energy in Australia? Again, you can read up a lot of this information was taken out from the internet. So the most latest information you can Google and find out. So what is some of the places that you can look? You can look for Australian Clean Energy Council, right? If you Google that's a good website to check. Australian Renewable Energy Agency, ARENA. That's a good place to check. You can just Google in general, Renewable Energy Australia. Some links will come up and you can do a bit of reading. And I think it's good to do that because you get the most current, up-to-date information about what is happening. So I encourage you to do that. So here, in this picture here talks about the electricity energy generation in 2015, 2016. So as you can see, 85% of electricity generated using fossil fuels, and only 15% has come from renewable energy. So what's the energy mix? So black coal contributes 44%, brown coal 19%, gas 20%, and oil 2%, right? Some diesel 2%, right? So that, if you sum up all that, oil, gas, brown coal, and black coal, that will come up to 85%. So, and 15% comes from renewable. A major part of that comes from hydro. Hydro contributes 6%. And there are a lot of hydro generation in Tasmania. Wind contributed to 5%. That's still a big amount. Bioenergy 1% and solar 3%. So that was the energy mix in 2015, 2016. Again, this information is available on the net. And 2016, 2017, you can see in the following year, the renewables have increased. It's up to 17% from 15, and obviously fossils have dropped a bit to 83%. And large, like we saw in the previous case, a large portion of the renewables are coming from hydro and wind. Hydro contributing 42% and wind contributing 30%. And here, some comes from small scale PV, 16%. So small scale PV is basically referring to rooftop solar on residential houses. Large scale PV, so large scale solar farms, because we know there are large scale solar farms contributing about 1.2%, and small solar thermal 0.1%. Some insignificant amount. So yeah, so this thing here basically tells what I just said. And in 2017, more than 35 projects were under construction. Renewable energy projects were underway. So there was a lot of activity starting even back in 2017, and lots of money going into those projects in the order of billions of dollars, about $5 billion. So what that means is that there is activity, there are projects, there are jobs in this space, right? That's what it means. And yeah, and that's important. So installation of rooftop solar, this has been growing since 2016. It's been accelerating, right? Lots and lots of customers taking up. In 2016, there were 135,370 installations across Australia, and this number has been growing. And renewable energy is now the cheapest kind of power generation that can be built today, less than both new coal and new gas-fired power plants. So it's cheap to build renewable energy plant. But renewable energy also comes with a challenge. And may I ask, what's the challenge? Reliability, intermittency. Because renewable energy is intermittent, right? Like, because if you take solar, well, we can only generate when there is sun, and also if there is a cloud cover, then all of a sudden the generation can dip, can drop. And same with wind. If there is wind, we can have energy, but when there isn't, then we can't. But our requirement for electrical energy may be constant. Maybe we need a certain amount. So that intermittency is an issue. So that intermittency also is linked to reliability. How is it linked to reliability? Because if supply and demand is not matched, then the network goes down. So a key enabler for renewable energy is storage. So if we can store energy, then that will allow more renewable energy to penetrate into the system. Yeah. So key enabler is storage, and cost of storage has been high, and it's coming down. So the more storage we have, the more renewable energy we can use. So Australia still relies heavily on fossil fuels, right? And the government has set, well, back in 2016, 2017, government set what we call the Australian renewable energy target. It's called RET, renewable energy target. And the target was to have about 23.5% renewable energy generation by 2020. So I would ask you to check if we have achieved the renewable energy target, and I think we have. It's about 24%, is it? You looked it up? There you go. That's what you guys all have to do. Just read a lot on the internet. I keep encouraging that, right? Because you will get up-to-date information on the net, and we just heard, like you just looked it up, so it's very current. You just looked it up. We have hit the renewable energy target. So Australia did set up this target, and we have met the target. Right. So because these lectures were written in 2016, and at that time we were there halfway to meeting the renewable energy target, and what, we are in 2021 now, we have met it. At the beginning of 2021, the goal was to meet the renewable energy target in 2020. So obviously we have met. So it's about quarter of the energy coming from renewable energy, which is not bad. All right, so this is what was going on in 2017 in various states. Summing up everything, there was 963 megawatts of renewable energy projects that was underway to generate, 963 megawatts from renewable energy, right? New projects. There's lots of investment, $7.4 billion, creating about 4,105 jobs, new jobs. So that's what happened in 2017, and there is a similar picture, perhaps more investments in subsequent years. Again, all this information is available on the net. It's a matter of digging up. This information came from, I think Clean Energy Council website. So just check those websites. Those information is there. You can read up. And I think is important to know, right, what is happening in your own industry. And And also, looking at this in 2017, most of the projects was happening in the eastern states, and investment in Western Australia was low. I think this may have changed now. So check those things up, because it's very important to know what are the projects that are happening, where those projects are happening, which companies are investing, right? These are general stuff, general knowledge. So you need to read this stuff. Obviously, I'm not going to ask this in the exam or final exam, but you're not here for the final exam only, right? Because when you go out, you go and talk to people, you need to know what is currently happening, you need to know who is investing, which companies. So you've got to read that stuff. It's there. Right? Because when you go to interviews, it's highly unlikely someone's going to ask what is complex power, can you calculate this and that, right? They're probably more likely to ask questions like this, which we don't cover here. But you can read it up. You need to read it up. All right. So you will also probably heard about the trilemma. What is the trilemma? Well, we want electricity to be affordable, right? Electricity costs have been going up, and we're not too happy to see big bills. We like to turn on the air conditioner at night when it's hot, because we can have a good night's sleep. But that costs money, and we don't want to pay that much. Yeah, and so affordability is important. We need the cost of electricity to be low. We want to reduce emissions, because we want to do some good to environment. Right? We don't want to produce a lot of greenhouse gases, so we want to cut down on our emissions. And we want reliability. We don't want to lose power. We want the power to be available, especially industrial customers. They can lose a lot of money. Imagine, mining companies losing power for a small period of time. That can be quite costly. So reliability is very important. So these are kind of competing goals, because we can reduce emissions if we have lots of renewable energy, right? But that can impact reliability if we don't have sufficient storage, right? But if you spend a lot of money, if you have lots of excess generation, spend a lot of money, yes, we can have reliability, but then there's an affordability, it will cost more. So, yeah.
Is making technology more affordable really just, based on things like government grants and research topic, or is there other factors outside that?
I think it's not just subsidies. Hi, Lijing, there's some problem, we can't broadcast it. We'll try during the break. Yeah. All right. So during the break, we can try see if we can actually help out the guys who are joining us online, so to be able for them to see the lecture slides. But I hope you all are actually which slide I'm talking about. So you have the notes, so you can hopefully follow what I'm saying. So yeah, it's affordability is not just through subsidies. Subsidies means you take money from somewhere else and try to reduce the cost of electricity. That's not what we are talking about. We're talking about actually bringing the cost down. Because if we can produce solar panels for cheaper, well, the cost of electricity comes down. If the storage cost, if we can reduce, then the cost of electricity can come down, the reliability can be improved. So it's the actual bringing down the actual cost. So if we can actually achieve all these three goals of emission reductions, affordability, and also reliability, well, that's what we want to achieve. Trilemma is how do we go about achieving all that. So to be able to achieve all that, we need the bright minds like what you have. So you will have to provide the solution when you go out and practice as engineers out there. How can we achieve that? It will come from your thinking. How we can advance the technology have greater reliability, how we can have low-cost solution without compromising on reliability. So that's the trilemma. All right, affordability. So let's talk a bit about the affordability. Now, electricity, right? We pay for electrical energy, right? So what is a unit of energy? Because if you talk about watts or kilowatts, we're talking about power. We're talking about power. So power multiplied by time is energy. So if we take kilowatts and multiply by time, by an hour, kilowatt hour is energy. And it's referred to as a unit of energy, 1 unit. So if you take your electricity bill, which I encourage you to do again, just go and check your electricity bill and check how many units of energy that you're consuming over a period of time. Usually you get the electricity bill over 2 months, right? Just check it, how many units. That it will tell so many units, right? And each unit at 28 cents. Around 28 cents is what you pay to Synergy per unit. So unit of energy is kilowatt hour is a unit of energy. And then, yeah, just have an understanding of how many kilowatt hours that you're using over 2 months. So that will give you an idea on average how many kilowatt hours you're using per day, right? How many kilowatt hours, how many units of energy you're using a day. And then you can think even more, right? Because you're an electrical engineer. You need to have good understanding of what's happening, your electricity usage at home. So you're using certain amount of units on average per day, and obviously you're not home most of the day during the daytime. You're using it during the morning time, and also you're using it during the night time. So have an idea how much units that you're using in the morning time and at what times. Because when you get up, you turn on the kettle, you turn on the toaster, you turn on a few lights. And at night, you do the same. You turn on the television, you turn on various equipment, right? You turn on the air conditioner. The fridge is running all the time. So just see if it matches up, the units. Because each of those devices will have a power rating. And you know how long you're operating these devices, equipment. So you can have some idea. Your lights are like 80 watts, 100 watts. And you know then how many hours you're keeping the lights on. So just you will have an idea about how many units of energy that you're using, and if it matches up with your average daily usage, just check that out, right? And then if you, and of course we also have a constant consumption as well, because the fridge is on all the time, some other things will be on all the time. So there's a base consumption as well, right? Base consumption as well. So check that up, and if you do that, you will probably notice there is a small peak usage in the morning and even a higher peak in the evening, at night. So it will be 2 peaks generally, right? 2 peaks. And there is a base consumption as well. Now somebody was talking about a duck curve. Now what is that duck curve? Now if we have more and more solar coming in, right? More and more solar, so that base consumption is going to be served by your solar. So during daytime your requirement is less, right? Of course some houses will be injecting, but in general if you sum everything up, the power demand during the daytime will continue to dip because we have more and more solar generation, right? And when the sun sets, again it will rise up. So the curve then looks like a duck, right? So it's called a duck curve, and that presents some problems because you need to, when there is no sun, when there is no solar generation, you will have to ramp up generation quickly, and also still there has to be investment into power plants simply because you have lots of solar. That solar is only utilized during daytime, but at night time there is no storage. You still need all those generators, right, to turn on. So in terms of the investment, the cost of electricity is still there. You still have some capital investment, right? And on top of that, you will have this requirement to ramp up quickly, right? So, so the duck curve presents some issues, right? So you can also read up on the duck curve, right? Say because you might go to an interview or something, and then somebody panel with us, do you know anything about the duck curve? So because they are kind of general kind of questions, so anyway, you need to be aware of these kind of things if you are going to be an electrical engineer. So I'm just pointing you to these important areas where you can do some further reading, which is important, right? Okay. All right. So now we said that the cost of electricity is about 28 cents a unit. We know unit is kilowatt hour. So what make up this 28 cents? Who are we paying? Because we know there are retailers, we know there are generators, we know there is a wholesale energy market, right? There are guys who are looking at the poles and wires and all the safety gear, right? So how does this 28 cents, what are the components, what makes up the 28 cents? So about 40 to 55%, like half, let's say, is the network cost. So we are paying half of that 28 cents to Western Power essentially, right? Good to know. Who are we paying this money to, right? About half we are paying there. Wholesale energy market costs. So 30 to 40%, about 1/3, half to about Western Power, 1/3 to actually buy the electricity. The actual cost of generating electricity, 1/3, right? Around 1/3. Then about 5 to 15, maybe 10% environmental policy costs, because if we are producing, if the electricity is coming by burning coal, so there is maybe a little tax or something that needs to be paid. So some policy, environmental policy costs around 5 to 10%, 15%. A residual component around 5 to 15% the price for retailers, their profits, and also losses. Because when we consume electricity, it's not only our consumption. Part of it is, small part of it will get lost, right, in the transmission and distribution. So about another 5 to 15% of the cost is for the loss. It is to account for the losses. Somebody's got to pay that, right? So that's what make up the unit price of electricity, right? You are an electrical engineer, right? So you need to know what a unit is. You need to know the consumption in the morning, at night, which units are consuming electricity, price of the electricity, unit price of electricity, and what makes up, what are the components in that, right? So all this important information you need to know. Yeah.
Why do we get the bill from Synergy and not Western Power?
Because the retailer is Synergy, we buy the electricity from Synergy. Yeah, and Synergy bills us for the whole lot, and they must be paying all the others. But these are government organizations anyway, right? Synergy, Western Power, right? But only one party sends us the bill, which is Synergy, because they are the retailer. And obviously, Synergy can't take that whole 28 cents. We will take a portion, we'll give a portion to Western Power because the network needs to be managed, right? If the network is not managed properly, then the generators can't send the electricity to the customers, right? So then we need to upgrade the network, right? Now this is a big issue as well. Like infrastructure costs a lot of money. Australia is a big country, right? Western Australia is vast, and people live far away. So we need to build infrastructure, poles and wires to get electricity to those remote places, and this costs money. Now this is where the new discussion comes in. Is it worth for Western Power? Is it worth to actually build these networks, lines going far distances to remote places with few people, or are we better off giving them standalone power systems or creating microgrids in those places with a weak connection to the grid? So you're not sending all the electricity, have a weak connection or isolated microgrid or standalone power systems. Is it more worthwhile to do something like that rather than invest on infrastructure, right? So if we can make this thing efficient, then the cost of electricity can come down, right? We can see 50% of the cost is going to for the electrical network, and the infrastructure is not cheap; it's expensive. Right. So this is where again you need to read about standalone power system, read about all those policies, people talking, different views and all that. Just read up. There's lots of material on the internet. It is actually quite interesting to read. Zoom is running there. Yeah, you can try to do. Yeah. So can we take a 10-minute break and we'll come back? So we'll see if we can fix this Zoom issue. So Zoom is running. So, and what I do is I usually just share content and I show screen, right? Yeah. And then usually I should be able to start broadcast, right? We were able to do it yesterday.
In office is okay, but in the venue it can't do that.
I've not seen the app on this before. Can we join Zoom on here?
Yeah, we can try. So what do I do? Okay, we will just...
You know what the details are?
It's
in there. So that's the
okay.
ID.
I join here, is it?
Yep, that's right. Join a meeting, yeah. 307 107.
Hang on a second. Meeting. I need to give the meeting ID. Sorry.
307.
307.
107.
107.
9279.
9279.
Yeah.
Yeah.
Click join.
Do I? What about?
You don't have to worry about that. Yeah. Just join. And the meeting password is 944 323.
944
323.
323.
Yeah.
Join.
Join with computer audio. Share screen. Start.
So do I need? I'm the host, right?
And how do we?
How do you?
Just more. Well, I just want to see what you want to share.
Okay, what I want to share is this.
Well, as far as I can tell, you're doing everything right. Normal practice is
Yeah.
I would get you to restart the iPad, or restart the Zoom session.
I see.
Do
That
you-
will kick everybody out, right?
Yeah, I don't want to do that.
Yeah.
Do you have this presentation on a thumb drive?
You mean they have the lecture slides?
They do have it?
They do have it, but if I write it, they won't see it. Like I will be writing stuff. So should I bring my other computer and see if I can? My laptop. If if we no, I will come. Because I need to bring a cable as well. I will try and go and bring that and see if we can do something.
Can't we do that?
Well,
iPad is problem.
it's an iPad issue. I don't think it's a Zoom issue. So
We tried exactly the same connection in the old days using another computer screen.
it's an iPad issue, and
Do you mind if we try my computer? And could you give me where's the Zoom?
okay, right, I can.
Can you give me the host privilege? Yep. And try it out. I have to use this easy. I have to use the
Not here, maybe from here. How do you? Oh, you go here and go Zoom and participants.
Or maybe we just can, yeah. Make the co-host.
Make a co-host, yeah. Yep. So if we then go,
Anyway. So Harold is picking up his laptop.
If you share the audio file, the online student said sometimes they can't hear. You better use the microphone in this thing to share it in the Zoom.
see, this microphone is only for this room.
Yeah, that's why I
And
said.
that's why if you use Zoom on here, this microphone will be shared by Zoom.
I think Harold put on too much one for the laptop will pass it up.
Does he haven't? Yeah. Because you usually use Zoom on this computer, and then you can share let me check that it's actually wired like that.
device is pick up the sound from the room, give them to Zoom. Yeah, I do that. I do that. We try this one. We temporarily disconnect this HDMI cable, and we enable the Zoom broadcasting, and then connect it in. Will that be working? No, not this one. From here. Let's try it.
You try it on.
Yeah.
Because it's sharing the screen.
And zoom it. And let's just start again. So share screen.
See, it's the best thing is if you run it on here.
And if you want to write something on the pad,
Okay.
using Zoom, they can show slides, but they can't give any notes.
Yeah, you're right. So,
Is that possible to find some solutions, or is it just a week one?
he'll have to negotiate that with Zoom. It's
But that one, that might be one. Laptop, not pad.
is that a touch? Yeah. Well, we can try the same thing.
Maybe next week. That's this week.
Yeah, it's yeah. Now, if there is a Zoom share, right, which only shares content, right?
We can share screen.
Yeah, but there's a feature within Zoom which only shares content.
Shall I run Zoom here and then connect the iPad there? The guys, if they get
Can you
kicked,
connect this one? Yeah.
if they get kicked out, can you ask them to reconnect? Not that. I would have to connect that. Yeah, this thing goes there
Into there.
into there, I think.
Yeah.
Can you tell them to reconnect if they get kicked out?
We will see it here. Okay, let's do it.
Ah.
Because this is connected to Zoom, so that's same.
So it's working, is it?
Yeah, but we still can't share. All I'm doing is confirming. I'm acting like another remote participant.
You can't share.
So,
So-
if you had the thumb drive with content on it,
Yeah.
so if
So
you
can-
join Zoom here,
Yeah. So I'll disconnect this. I want to share that. I will run Zoom here.
oh no, not start. You have to join this meeting.
Is it?
And
Because if I join,
cancel that.
have I joined? Am I connected to
Just check this one here.
this one?
Click that, yeah. It's a different meeting ID, so you can close that.
I can
leave.
leave.
And meeting for all, yeah.
Yeah.
Now go join.
So am I the host then?
We can make you the host. So
What meeting?
it's 307
307
107
107
9279.
9279.
And the password is 944
So what is that? Do I put the password there or?
Click join. Oh, yeah, you're in.
Join. So I can. Is that everyone? So everybody's there. So what if I? So am I the host?
Let me just turn the volume down here.
Yeah. 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 Okay. Okay. And then how do I can I want to share. So can I share from here? Like I
don't
will.
know if you can
So
share that
so
way.
can I
So if you share from here,
yeah, I want to share from there. See, I want to choose this one.
okay, try that. Click share. Trust, yeah.
I can't click. Ah, hang on, something. No. What's happening?
Trust.
Can do.
So we'll go just one more time. Just it's
It's doing something.
it's yeah.
I usually am able to do that from home.
Are you? Okay. Maybe a restart is in order or something like that.
So should I restart that? I
Yeah,
can.
I think you can.
So I will disconnect the Zoom from here.
Yeah.
Else. So I want to end. I want to leave meeting.
Yeah, leave the meeting.
Uh,
Sign
I-
and leave.
So
yeah.
can I?
Yeah. Okay, co-host, yeah.
So I'm there.
Yeah, so now you have to restart this. But you need to,
Yeah, I need to do something like that. Complete restart, right?
well, I've never seen anyone share via the cable.
Really? I share what I can.
I've
Really?
not, it doesn't mean to say it can't be done.
Yeah.
It's something new for me.
I see. Right, right. Because when I say share, then this appears, and I just
Yeah.
click that, and off I go. Like
It should be, but so if we go, just unplug this for now.
yeah,
So let it do a
Yeah.
refresh,
yeah,
and we'll try again.
yeah. Okay. So we will. We don't do Zoom here. We just okay. So must be a university firewall or something.
It's trying, isn't it?
Yeah, it's strong.
Can we try something else? Can we share something else? Let's try. Is there anything that I could just
You can share that, like that's the sharing.
desktop one?
Yeah, let's share the calculator.
Okay.
There you go.
That's fine.
Yeah.
Stop
So
share.
it should do this.
Yeah. Here we go. Share. And we'll plug this in. iPhone.
Why? Yeah, AirPlay. I mean, this is table is better.
It is better.
just go. They will have to listen just voice,
Yeah.
right? I think I have to do. Yeah.
Next time, if you use Zoom on here,
Yeah. Now what happens now? I will keep the Zoom there, and I can just work on that.
yeah,
They will hear.
they will hear. They won't be able to see.
Okay, so I can just disconnect that.
So,
I will connect this, right? They can hear, right? And
I
I
assume they can.
yeah, I assume they.
Because this microphone here
Yeah.
picks up your voice.
Which microphone?
This microphone that's on
Yeah,
here
yeah.
picks up your voice.
And
this microphone is for in the room.
sorry, this microphone is.
It's for in the room. Okay, so
Yeah.
this one you need to project your voice in the room.
Yeah, yeah.
And
And okay, some microphone.
when you're holding that, there's a microphone here,
Yeah.
right? And that will be the voice for the people remotely.
Okay, for people, this is for the room,
Yep.
and what is for the people in remotely?
There's a
Microphone there,
Yeah.
but okay. So it's going through here because it's connected there. This is just to give them the.
This was just to try something.
This is just to give them the Zoom.
Yeah.
Or they're picking up the voice from this.
That's not up there yet, and it should be.
What is up there?
That's not.
Voice. Why isn't it?
Why isn't that going up there?
That's strange. What if I do that?
That's what you see here.
Yeah. Try that.
Just try something else while, if I might.
Yeah. Will you try that?
Something happened with your iPad, yeah? put it up here.
That's strange.
Yeah, because it should just put it up there like that.
Yeah.
Do you have another one of those? No, I haven't got one. Because that. Let me try one other thing.
Sorry? Visualizer?
That means the cable's working.
Cable's working, right?
Yeah. Something to do with settings in the laptop. It's in.
What is that?
That's the symbol to show that's connected.
And now it's not there.
It's tried to connect and it hasn't been able, because that symbol should be there
Yeah.
whenever you got that connected.
So what's the problem? Because that doesn't work. Maybe I go to LMS here.
What do you want?
The slides.
Slides. Yes, go to LMS, please.
LMS. Give us just under 5 minutes because that what was working doesn't work.
Maybe I can do that. You want on this computer?
Yeah, yes. I just do it from this computer.
I don't know. Yeah. See, the adapter's okay.
Adapter is okay.
Yeah, because I've got my phone up there.
Then what is the problem?
It's something to do inside the iPad. Yeah.
Okay, maybe I need to buy a new one.
I'm not certain exactly what it is, but
Thank you for your help. Anyway, yeah. Well,
it doesn't feel like I've helped much at the
but
moment.
that's okay. That's okay. We'll continue on and see how I go. Thank you very much. All right. Let's begin again. Well, what was working before is not working now. So I was going to write stuff on the iPad because I want to show some calculations. But unfortunately, I can't do that because I can't connect the iPad. Sorry about all that. That's beyond me because the computer support, UWA, can't help me. We have to, what was working doesn't work anymore, so I don't know. But all these things iron out and fix because we're trying to do too many things at the same time and it doesn't work. All right, so we've talked about the cost of electricity, right? We talked about the cost of electricity and we talked about a unit of energy. And the unit of energy currently in Western Australia, Synergy selling it at around 28 cents for us, and we also understood what make up that 28 cents. Now, over the years, right, over the years, the cost of electricity has been going up, as you can see, from 2009 to 2017 for various states. You can see green South Australia, blue Victoria, red New South Wales, and so on. You can see all the states. The cost of electricity has been going up in general, right? And the cost of electricity is not the same in all the states, but more or less similar. But overall, it's been going up. But I think in recent years, it's been quite steady and flat. Now, okay, with reliability, I think you may have heard a couple of years ago. I mean, South Australia has a huge, high proportion of renewable energy, around 50% renewables, I think. Again, you can check up that number for yourself. I think it's about half. And we had a few reliability issues. The network went down a couple of times, and some forced load shedding had to be done because, that amount of demand couldn't be met. So had to, reduce the load on the network, and some customers had to come out of the network, and that's not good. So, yeah, we know reliability is important, and if for high proportion of renewable energy, we need sufficient storage to ensure reliability. And emissions reductions are necessary. So it's the three objectives that I highlighted that we're trying to achieve: reduce emissions, lower cost for electricity, and achieve reliability. So how we go about doing that in future, hopefully we can achieve that, and I'm sure you people in the class will have something to contribute to that. Right. So vision for a future electric grid. What will a future electric grid may look like? A seamless, cost-effective electricity system from generation to end user, capable of meeting all clean energy demands and requirements with a significant scale-up of clean energy, renewables, natural gas, nuclear, and clean fossil. A universal access to customer participation and choice. So we would like in the future grid the customers to have more participation, to be able to generate electricity, inject electricity into the grid, to participate in demand response. In other words, change load based on a cost signal. So the cost of electricity to vary during the day, and to be able to minimize electricity costs by changing the load of the day, utilizing energy when the cost of electricity is low, and utilizing less when it's high. So we would like to see more customer participation. Then again, if you have excess energy, can customers sell electricity to others who require it, right? Peer-to-peer energy trading. So all this we'd like to see happen. So universal access to customer participation and choice, including distributed generation, demand-side management. So demand-side management, I talked about it. It's like you changing your load to minimize the cost of electricity. Electrification of transportation, that's using electric vehicles, and energy efficiency. With electric vehicles, the electric vehicle has a battery, so even to have vehicle to home connection and home to vehicle, and also vehicle to grid and grid to vehicle connection. So vehicle to grid is when the energy in the battery being injected to the grid. Vehicle to home is energy being injected to home to serve your needs, and of course the other way around as well. Grid to vehicle is taking energy from the grid, and home to vehicle is like when you have solar generation to charge up the batteries in the car. Right. So a holistically designed solution including regional diversity, AC-DC transmission distribution system, because the electric grid doesn't necessarily have to be an AC grid. It can be DC as well. So maybe a hybrid grid with AC and DC connection, because some of the your power requirement, for example, your laptop, you don't need AC. It goes through a DC to actually power the laptop. So why have all those energy conversions and lose energy in the process? Why not have a DC grid or DC bus as well, where you can connect the DC devices into that? A two-way flow of energy and information, because the traditional grid was designed for one-way energy flow from the generation source to the customer, so it was designed to do that way. And the future grid may be a two-way, because energy has to flow from the customer to the grid as well. And currently there is a project going on, which is called Project Symphony, implementing the WA Distributed Energy Resource Roadmap. It's called Project Symphony, funded by Australian Renewable Energy Agency, which we contribute to that as well from UWA through our research. That has to do with when there is excess energy, well, you have current flowing in the reverse direction, and the network is not designed to do that, right? So how, and one of the consequences of that is that the voltage, because rises in the distribution network, because now current flows in the reverse direction at the bus bar where all this distribution line connects has a fixed voltage, and end of the line, now we have an increase in voltage because current is flowing in the reverse direction. So, and these line specifications, the voltage needs to be in a particular range, and that range, that voltage profile on the line when there is reverse current flow can violate those specifications. So there is some work to be done, right? Some work to be done to make sure that we support two-way energy flow, right, in the future grid. And of course, we talked about reliability, and security is also important, because the electric grid is now connected to the net. Lots of information being exchanged from the grid and the net. So there has to be these things need to be looked at in a future grid. Okay. So here is just a picture of a future grid. So you can see at the center there is analytics. So it's lots of information will be generated, especially if you want to do demand response. Because at the moment, right, if you have an old electricity meter, I mean, that will simply record the electricity usage over a period of time. There is no information about the real-time usage of electricity. So somebody will walk in and see, okay, you use so many units of electricity over the past 2 months. That's it. How you use that electricity, no idea. Yeah. Like what is your usage pattern? There is no information about that. Only an average usage that is available. So if we are going to have information about your real-time usage, there will be lots of information. There will be a huge amount of analytics, data that need to be processed. So you can see in this future grid, analytics will play a very important role. And in this picture, we can see it in the middle. We may see nuclear power plants, hydro, maybe still some coal generation, large-scale storage batteries, right? Because with high proportion of renewables, we know the battery storage is important. Solar, PV, like solar farms, of course, rooftop solar as well, natural gas production and electricity generation, then of course substations where voltages can be reduced from high voltage to low voltage or in the reverse direction, right, substations, and other forms of electricity generation. So renewable energy will be a key component of that, and there will be a lot of data analytics built into a future grid. So want to contribute to a better energy future for Australia? I think it can start from this course. Your interest you can develop from here. All right. So let's go through let's review some information that you may already know. Phasor representation of signals. So you know that voltage and current signals are sinusoidal in nature on the electric grid. So it may look, we can represent a signal using an equation like that, Vmax cos omega t plus theta. So what is Vmax? Vmax is the maximum amplitude. Vmax divided by root 2 will be the RMS value, the effective value of that, that voltage signal, right? That max amplitude divided by root 2. So then omega is the angular frequency, and we know the frequency is 50 hertz, so omega is radians per second, multiply 50 by 2 pi to get the angular frequency, right? And what is theta? Theta is the phase angle, right? So it has to do with where the signal begins, where the origin is, the phase angle, right? So if you have cos theta, you know the shape of the signal, right? We'll have the maximum at time t equal to 0, right? And then you know the shape of a cos curve, and then if it's cos omega t plus theta, then you know there is a phase shift. The maximum won't happen at t equal to 0, it will be at some other place, right? Okay, so we understand that, we know the RMS value. RMS value, we will represent that as absolute value of V, if you like, in the notations. So Euler's identity Ej phi is cos phi plus j sin phi, right? You've seen that in maths. So if we say Vt is Vmax cos omega t plus theta, right? We can then say this is root 2 times the RMS value, because root 2 times the RMS value, right, is Vmax. Then it's the real part, cos omega t plus theta, is the real part of e to the j omega t plus theta, because e to the j theta is, or j phi is simply cos phi plus j sin phi. So what is cos phi? Cos phi is the real part of e to the j phi. So it's something simple. Anyway, you know this stuff. And how do we represent using a polar form? Using polar form, we can just represent the signal V as the RMS value and the phase angle theta. So what does that really mean? See, if I represent the voltage as the RMS value and the phase angle theta, when you see that, you immediately know what Vt is. Vt has the RMS value multiplied by root 2 as the amplitude. Cos omega t is the, well, the frequency times the time, plus theta. So by just knowing the polar form or the exponential form is just that theta, we write it as e to the j theta, right? We immediately know how to translate that back into a trig form, right? So that's it. We already know how to translate that to a trig form. So when you, just to keep it extremely simple, if you have Vmax cos omega t plus theta, it's omega t is like, we know omega exists and we know the value of it. Amplitude we know, divide by root 2, well, that's the, in the polar form that V is that, and theta is the phase angle. That's it, right? And we can go in both directions. When you know the polar form, we know the trig form, trigonometric expression, and if you know the trigonometric expression, we can translate it to the polar form as well. All right, so I just keep that. Impedance and admittance. So impedance is just the resistance and a reactance, right? The real part. If you take an impedance, impedance has a real part and an imaginary part. Real part is the resistance. Imaginary part is the reactance, right? And if you summing the resistance and the reactance, they are connected in series, right? So R is connected in series to JX, right? And that's the impedance. R plus Jx is the impedance, resistance is R, and reactance is X. So when you're talking about the reactance, the J component is not there. It's just the X that we are talking about. Reactance is X without the J component. Okay? And then, so across point A and B, you can see point A, point B. Across point A and B, you have R in series with X, right? Jx, because, and then the impedance is just the sum of the two. And the admittance is the inverse of impedance, right? Is 1 on ZB, right? Yeah. So if it's 1 plus J is the impedance, 1 over 1 plus J is the admittance. You know that. Now, admittance, right, is a complex number, just like impedance is a complex number. Admittance is a complex number as well, right? Because if you invert a complex number, you will get another different complex number. It has a real part and it has an imaginary part. The real part is what we call the conductance, and the imaginary part is what you call susceptance, right? So admittance has conductance, which is real part, and susceptance. So this admittance, if you're summing admittance, you're actually thinking about elements in parallel. So if you're talking about impedance, you're thinking about elements in series. If you're talking about admittance, you're thinking about elements in parallel, right? So if there are elements in parallel, it's convenient to think about admittance. If you're thinking about elements in series, it's easier to think about elements connect. If you're thinking about impedance, you're thinking about elements connected in series. So if you have Z1, if you have one element in series with another element, right? So this, let's say the first element, then it's convenient to think about impedance. So we'll think about impedance for the first element. We'll think about the impedance for the second element, and we sum them together. We can sum them together, right? If you have two elements in parallel, it's convenient to think, okay, I'm not going to think about impedance of this and impedance of that, which are connected in parallel. It's convenient to think of admittance of the one element, admittance of the second element connected in parallel, and you can just sum them together, right? Okay. So, yeah. So what is conductance? Conductance is the inverse of resistance, 1 on R, no sign change. Susceptance, what is that? It's the inverse of reactance, but there is a sign change. It's negated, right? So that's, again, a clear idea of all these terms as an electrical engineer would be important. You need to know what is impedance, what is admittance, right? Resistance, reactance, conductance, and susceptance. So you're an electrical engineer, you need to very clearly know what these things are. And those are the definitions, the terms. And you know that if you have elements in series, it's easier to think about their impedances, so you can add them. If there are elements in parallel, it's convenient to think of their admittances, so you can connect them in, you can just sum them together, which are in parallel. So that's exactly what we are talking here. So if you have an inductor, then your XL is XL is just omega L, right? So if you have a resistor R in parallel with an inductor, right? So inductor is J omega L, right? Omega L is the reactance, right? So it's now convenient for us to think of the individual admittances of those elements. So resistor, instead of thinking of a resistor, I'm going to think of it, if the elements are connected in parallel, instead of thinking resistance, I'm going to think about conductance. So I'm thinking 1 on R, right? And the inductor, I'm going to think of, instead of thinking about reactance, I'm going to think about susceptance, which is minus 1 on omega L, right? And then I can add them up. right? I can add them up. So G plus JB. What is G? G is 1 on R. JB. What is B? B is minus 1 on omega L. Right? So we can add them up. G plus JB. If those elements are in parallel, it's convenient for us to think in those terms. Yeah? So that's I mean, you should think about this a little bit. So the first one says series, right? Z. So I'm thinking about two elements connected in series. So it's convenient, okay, I'm going to think this is a resistance, and reactance. Right? Resistance and reactance, because then I can add them up, and that's impedance, Z. If the resistor and inductor in parallel, it's convenient to then think conductance, which is 1 on R, right? Because resistor and resistance are two different. Resistor is an element, right? When it's in series, I'll think about resistance. When it's in parallel, I'll think about conductance. Right? Inductor, if it's in series, I'll think about reactance. If it's in parallel, I'll think about susceptance. It's convenient to think like that. So that's what these two lines are saying. So I think it's important for you to know that. And susceptance, when you're taking the susceptance, you invert omega L and you change the sign. Right? And you just simply add the two up. Well, if it's reactance or susceptance that you are adding, well, there is a J term that you need to incorporate. Right? That's why you have JXL and you have JB. Right? Okay? And you can do the same for capacitance. Capacitor. When they are connected in series and when it's connected in parallel with a resistor. If it's connected in series, well, resistor, I'm going to think about resistance, right? XC is the reactance, which is minus 1 on omega C. Right? On the other hand, if I'm thinking about susceptance, I invert that, change the sign, so it's omega C, right? J omega C, right? J omega C. And this G becomes 1 on R, conductance, right? So that's pretty interesting. Know about the definitions, right? Because as an electrical engineer, you cannot not know those terms, right? And then think about this series and parallel connection. So it becomes very clear in your mind how those definitions link to actual parallel connection and the series connection of those elements, right? So when you think of resistor is actually the actual physical resistor. Resistance is the property, because a resistor, you can think about resistance or you can think about conductance, right? So when you have an inductor, you can think about the reactance or susceptance. Capacitor, same, reactance or susceptance. And how you think about that depends on how it is connected, whether it's connected in series or parallel. Right? Think about that. It's interesting. Everything is interesting, isn't it? All right. So, impedance, right? Impedance is a resistor and maybe an inductor in series, right? So it's a complex number, right? So what is an impedance? Impedance can be like 1 plus J, right? 1 plus J. 1 plus J can have a polar form. What is it? Root 2 angle 45. That's what that is saying there, right? The first line is saying that, root 2 angle 45. But of course, you're writing in abstract form, but that doesn't matter. I'm explaining it to you, right? So, we're talking about R plus JX, right? What is the magnitude of Z? Well, we know that complex number, if it's 1 plus J, then it's the square of 1 plus the square of 1, square root, right? Square of X, square of Y, square root. That's it. R square plus S square square root. And what is the angle? Angle is tan inverse y on x, in this case x on r. Complex numbers, right? And the same thing you can say, because when you're talking about admittance, admittance is a complex number. What is that complex number? G plus JB, right? So it has a amplitude, which is the square of G plus square of B square root, and it has an angle, which is tan inverse B on G. The same. It has a, we're talking about the impedance or admittance, it's just complex number, isn't it? Just two different complex numbers. And it has phase, it has a amplitude, and it has a phase angle. That's it. That's all that is saying. When you have a complex number x plus jy, I hope you know the magnitude is square root x squared plus y squared. Angle is tan inverse y on x. Right? I hope you remember that. Right. That's a very good point. So the yeah. So the angle. So let's think about. Okay, that's a very good point, right? So impedance. What is impedance? Impedance is a complex number. Let's think about in Cartesian form, right? X plus jy, r plus jx, right? That's an impedance. Okay, this gentleman is saying, is a very good point. What is admittance? Admittance is the inverse of that, right? You invert it. 1 over x plus jy. Okay. Does that give a lot of information? Well, it gives some. Let's think about it in Cartesian polar form. What is impedance? Impedance has a magnitude and has an angle, right? Then, what is admittance? Admittance is the inverse of that. So all you have to do is invert it, right? The amplitude gets 1 over. Angle gets negated, right? Angle gets negated. So that's the point you're making, yeah? Something like that.
It's just kind of like you end up just because being 1 over x and 4, you kind of end up being like if say then the angle of z was 30.
Yeah.
And the angle of the evidence would be 60 because you just swap the x and y coordinates around with x and r, your x and y coordinates, and b and d mathematically would be the opposite.
Or is it become minus 30? If the angle, yeah, if the, let's say impedance is 2 angle 30. So the admittance is 1 over 2 angle 30, right? So then 2 in the denominator goes to the top, becomes minus 30, and the magnitude becomes a half. Right? Think about that. Yeah, think about that. Right. Okay. So let's move on. Here is a very simple example, right? You have seen this in first year, so I don't even have to go through this too much. Anyway, we have this signal Vt, square root 200 cos omega t plus 30. Frequency is 60, so omega is 2 pi 60, right? Then, okay, the voltage signal in phasor form will have an amplitude of 100 and an angle of 30 degrees, right? So we will have 100 as the magnitude here, and the angle is 30, right? Resistor is R, it's connected in series, so it's easier to think about impedance, right? L is 7.96, so reactance is going to be omega L. Omega is 2 pi times 60. L, we know the number there. Of course, it's in millihenry, so you need to multiply by 10 to the negative 3, right? So we know the value of x. So the impedance is going to be resistor plus j times that x that you calculate, right? We can write it in polar form, which I'm not going to do, right? So the polar form is going to be phi angle 36.9, right? So then we want to calculate the current. Voltage over the impedance is the current. They are in polar form, so we can easily divide and multiply when complex numbers are represented in polar form, right? And easier to add and subtract when they're in Cartesian form. But here we are dividing, so polar form it's easier. We can divide in the amplitudes we divide, we'll get 20. The phase angles you can subtract. So you get minus 6.9 as your phase angle. So that's the current in polar form. Now, if you want to go back to trig form, you know how to go back to trig form because magnitude multiplied by root 2, that's your amplitude, cos omega t plus your phase angle, which is minus 6.9. And that's the current in trigonometric form, right? Okay. So that's trivial. That's a simple circuit in with two elements in series. Now, this one here, we have two elements in parallel, then what I was talking about. So the resistor, instead of thinking about resistance, we are going to think about conductance because they are in parallel. So we have 1 on R, 1 on 4 as our conductance, right? Then inductor, we are going to think about susceptance. Instead of omega L, we are going to think about minus 1 on omega L because susceptance, you have to negate the sign and invert omega L. So when we do that, minus 1 on omega L is minus 1 on 3, right? So then what is the admittance? Admittance is 1 on R4 minus J 1 on 3 in Cartesian form, right? Minus J 1 on 3 in Cartesian form. And then you can put it in polar form. Polar form is going to be, well, the real part, which is G squared, imaginary part, which is B squared, square root. What is the angle? Tan inverse, the imaginary part over the real part, and that's the polar form, right, for admittance. So we want to know the current. Voltage times the admittance is the current, right? V equals IZ, I equals YV. And we have them in polar form, you can multiply and you have the answer. So two very simple examples, but illustrates the definitions that we talked about. So although it's simple, just think about it. It illustrates what we've talked about before, our definitions of impedance, admittance, resistance, conductance, reactance, and susceptance, right? As electrical engineers, you need to have absolute clarity on this, right? So think about that. All right, complex power. So instantaneous power, PT. So here we are thinking about trigonometric representation of currents and voltages because we are talking about instantaneous power, PT, right? So that means we need to take the voltage signal Vt, current signal It, and you multiply together. So you have Vmax cos omega t plus theta, Imax cos omega t plus gamma, right? We multiply them together. We use some trig identities, right? You've seen these trig identities in year 12, and I'm sure, or university and year 12. We can simplify that. So when we simplify that for instantaneous power PT, we get this expression. And if you think about this expression, what is this expression? This is a sinusoidal curve. The frequency of PT is actually double the frequency of the current or the voltage, right? The current frequency is omega, voltage frequency is omega because you have omega t, and here if the frequency is double, why? It's not omega t, it's 2 omega t. So omega is being doubled. It's 2 omega when we're looking at the power, right? It's doubled. So this is sinusoidal. The average value of this term cos 2 omega t plus theta plus gamma is 0 because it's oscillating about 0, right? And if you consider the other term, cos theta minus gamma doesn't have a t term. There is no time dependency there. Theta is a constant, gamma is a constant, right? So it's a fixed value. Cos theta minus gamma is a fixed value. cos. What is theta? Theta is the angle of the voltage. What is gamma? Gamma is the angle of the current. So it's the angle of the voltage minus angle of the current. Cos of that is what we are looking at. And then gets multiplied by V max, I max divided by 2. V max over root 2 times I max over root 2, right? So you are multiplying the RMS values of voltages and currents, right? Multiplying the values of voltages and currents, multiplying that by cos theta minus gamma. Theta is the angle of the voltage minus the angle of the current, right? And so that is the average value of PT. Average, because we have a constant term, which is what I'm talking about there, and we have an oscillating term, which has an average of 0. So the average value of PT is that magnitude of voltage, magnitude of current, of course the RMS values times cos theta minus gamma. So that's the average power. I cos theta minus gamma. So this is called average power. It's also called active power. So the average power and active power are the same. Right? It's average power and it's also called active power. Right? They are the same. Now, what is complex power? Because we know that voltage has a magnitude and an angle and a phase angle, right? In polar form, V angle theta. Current is the same, is a complex number. It has a polar representation, which is I angle gamma, right? So if you take the conjugate of the current, so conjugate is you negate the angle. So if you have I, you negate the angle, that's I star. So if you do Vi star and you multiply them together, because you multiply in two complex numbers. When you multiply two complex numbers, you will get another complex number, right? And that complex number will have a real part, it will have an imaginary part, right? When you multiply two complex numbers, you get another complex number. Complex number has a real part and an imaginary part. So Vi star is a complex number. The real part is what you call active power. Imaginary part is what we call reactive power, right? Active power, what are the units? It can be watts, kilowatts, megawatts, etc., right? Reactive power, what are the units for reactive power? Is var. Vars or kilowatts or megawatts, right? Vars, kilowatts, megawatts. Now, so you know active power, you know what is reactive power. So you take Vi star, right? So when you say Vi star, what are we actually talking about? V is the voltage difference, isn't it? Voltage difference across an element. We're talking about voltage, so this is an element, right? Current is flowing through that. Voltage drops in the direction of current flow, right? Because when you say Vi star, V is just a symbol, I is just another symbol, what is it, right? But we need to think, picture it, element. There's a voltage drop, current flows, right, through this element. And the voltage drops in the direction of current flow, right? Okay. This voltage, we have a polar representation. I mean, the voltage drop, I mean, let's think about a real number. It can be 10, it can be 20. But when we are working with circuit with not only resistors, but resistors, capacitors, and inductors, we know we're going to represent this voltage with not only a real number magnitude, but also a phase angle, right? So voltage is don't think of it as a real number. It's in polar form. It has a real part and an angle. We have current. Current again has a magnitude and a phase angle, right? If the circuit was just resistors only, for voltage you will have a number, a real number. Current you will have a real number. But if the circuit has resistors and capacitors and inductors and sinusoidal source, we need to think not just real numbers, we need to think of numbers in polar form or complex numbers, right? So when we are talking about voltage and current, you are talking about voltage across an element, current flowing through it, And when you do Vi star, that's the complex power associated with that element. Because when you do Vi star, that's a complex number. It has a real part and an imaginary part. The real part will be the power consumed, the active power consumed in that element. And the imaginary part is the reactive power consumed in that element. So if you get a positive number for the real number, the active power is consumed. If you get a positive number for the imaginary part, the reactive power is consumed in that element. If you get a negative number for your imaginary part, that means you are generating reactive power, right? Now, if you do Vi star for a generator, then the real part will be negative, meaning that it is generating power, right? Because remember, through a generator, your current is actually flowing from low voltage to high voltage. Whereas in the resistors and other elements, voltage is flowing from high voltage to low voltage, right? So when you do Vi star for a generator, you will get a negative real part and a positive or negative imaginary part. The negative real part suggests to you or us that it is generating active power, right? So the sign convention that we are using, a positive, when you do Vi star, a positive number implies a consumption. Consumption of active power or consumption of, right? Okay. So active power is a real number, reactive power is a real number, but complex power is a complex number. It's active power plus J times reactive power, right? J times reactive power. Because if I'm looking at reactive power doesn't have the J term in it. Reactive power is the imaginary part of the complex power, right? Okay. So we have now talked about active power, which is P. We have talked about reactive power, which is Q, which you get when you do Vi star. When you do Vi star, you get P plus JQ. Remember, reactive power is not JQ, reactive power is just Q, right? And complex power is P plus JQ with the J term in it. That's complex power. So complex power is S. Magnitude of the complex power is what we call the apparent power. And what are the units for apparent power? Apparent power or units for what are the units for complex power is volt amps, because you're simply multiplying voltage and conjugate of current. Volt amps or kilovolt amps or megavolt amps, right? That's what we're doing. Now, okay, so here we need to define what you call power factor. So there is voltage. Voltage is V, magnitude V angle theta. Current, magnitude I angle gamma, right? When we're talking about voltage and current, we are now imagining. We are imagining an element, and it's the voltage across that element, and it's the current flowing through that element, right? Otherwise, we are just, what is V and I? So we have to imagine, right? And we know what theta is. Theta is the angle of the voltage. What is gamma? Gamma is the angle of the current. So if you take the difference between the angle of the voltage and angle of the current, if you take the difference, in other words, theta minus gamma, and you take the cos of that, cos of the angle difference between the voltage and current, that's what you call power factor. Right? That's what you call power factor. Now, when you take cos of that angle difference, whether you take cos of a positive angle or cos of a negative angle, you're still going to end up with a positive number, right? But that angle difference can be either positive or negative, depending on whether current leads the voltage or current lags the voltage? If current lags the voltage, right, angle difference is positive, right, and it's a lagging power factor, right? If the angle difference is positive, it's a lagging power factor. So this is what it means. If theta is bigger than gamma, angle difference is positive and it's a lagging power factor. So when you state the power factor, it's important to tell whether it's leading or lagging. If current lags the voltage, it's a lagging power factor. In other words, the angle difference is positive. If the angle difference is negative, right, current leads the voltage and it's a leading power factor. It's a leading power factor. So that's what is there. So you know about power factor. So power factor has to do with the angle difference between the voltage and the current, and you need to take the cos of that, and we have to state whether it's a leading power factor or lagging power factor. If current lags the voltage, then the angle difference is positive and it's a lagging power factor. And we can say the same thing about leading power factor, right? If the current leads the voltage, angle difference is negative and it's a leading power factor, right? Okay. So when you're talking about power factor, we are really thinking about an element, voltage angle and a current angle for that corresponding element and taking the cos of that. So always try to imagine the circuit with the symbols. It makes more sense then, I think. All right, so that same thing can be seen. Here you can see the voltage leading the current. So the angle difference is positive and it's a lagging power factor because current is lagging. And the other case, you see the current leading the voltage, angle difference is negative, angle of the voltage minus the angle of current is negative, and it's a leading power factor in this situation, right? All right. So this phi here is the angle difference. Phi there is the angle difference. So this is what you call the power triangle, right? Phi there is the angle difference, angle of the voltage minus the angle of the current. And P on the horizontal axis, Q on the vertical axis, right? That's what you call the power triangle. And if you draw Q on the vertical axis, P on the horizontal axis, and connect the triangle, that angle that you see there is the power factor angle, angle of the voltage minus the angle of the current, right? If P and Q are both the same sign, it will be a lagging power factor. If P and Q are different signs, then it will be a leading power factor. Might be worth writing that and then thinking about that. If P and Q are the same sign, I'll tell you why also, right? Think about an inductor, right? Current lags the voltage, right? Current lags the voltage. So if you have voltage across the inductor, right, is V angle 0, let's say, right? Current lags the voltage in an inductor, right? So the current through the inductor would be I angle minus theta, right? V angle 0 is a voltage across it, right? So if I do Vi star, I need to negate the angle of the current, right? Negative theta becomes positive theta. So when I do Vi star, P is going to be positive, Q is going to be positive, right? So both P and Q have the same sign, and it's a lagging power factor because current lags the voltage in inductor, right? So you can think about this like that, right? So do some thinking. I mean, it's some basic things you may know, but I think you can think more to have more deeper understanding, right? Do deeper understanding. Think like that. And so inductor consumes reactive power, right? Inductor consumes reactive power. And you can say the same thing, opposite thing for capacitor. If you do Vi star, you will have a positive, you will have Q negative. Q will be negative, not positive. If it's a capacitive load, Q will be negative. So what does Q negative means? It generates reactive power. So inductors consume reactive power. Capacitors generate reactive power, right? Capacitors generate. And resistors will consume active power. No element can actually generate active power. Only a generator can generate active power, right? But some elements can generate reactive power. Capacitor can generate reactive power. All right, so here, a load, complex power, a load draws 100 kilowatts with a power factor of 0.85, leading power factor. So leading power factor means then Q must be negative, right? Because if P and Q have the same side, then it's a lagging power factor. If P and Q has opposite signs, then it's a leading power factor. So here, this is a load, it's drawing, so P has to be positive, right? Then Q must be negative because it's a leading power factor. So we already know that, right? And so we need to determine everything, right? So we know the power factor, right? So apparent power times VI cos theta. Apparent power times power factor is P, right? So we know P, we know power factor, right? We can find the apparent power, right? We can find the angle because we know cos theta, we can find theta, but that theta, we have to make it negative. Theta has to be negative because it's a leading power factor, right? Yeah, because power factor angle is the angle of the voltage minus the angle of the current, yeah? So if it's a leading power factor, the angle needs to be negated. It's negative. It's not positive. Yeah. But when you do this R cos, we have to introduce that negative sign there because we know it's a leading power factor, right? Okay. So that's why that negative sign for phi, the negative sign we introduce. Yeah. So that's an important point, right? A very important point. So when you take the sign of a negative angle, you get the negative Q. If that angle was positive, when you take the sign of the positive angle, you get a positive. And if P and Q are both positive, it can't be a leading power factor because it's a lagging power factor, right? Okay, so that's that, right? So I think you can follow the calculations there. I'm just pointing out an important point. Right? I'm stating an important point there. Because you might wonder why where this negative sign came from. Right? You know where it came from. Because it's a leading power factor. If it's a lagging power factor, you wouldn't have that negative sign there. Right? Okay. So, power consumption of devices. So, if you are talking about a resistor, right, resistor only, so your Z is R plus J0, R plus J0, right? And if you do VI star, then we're simply going to get I squared magnitude I squared R. And that we know, right? Power consumed in a resistor is the current squared times R. And we can see that, we can derive that from our general expression VI star. Right? Because V is IZ and resistor is simply R. So we have V equals IZ times I conjugate. I times I conjugate is magnitude I squared times Z. Z is R. So you simply have I squared R. And also we can write, since we know magnitude V is equal to magnitude I times R, right? We can also derive the other expression. Power is also magnitude V squared on R. We can derive that as well, right? Starting from the general expression. Okay? So, inductor, Z is JXL or J omega L, right? So, complex power is VI star, V is IZ, I times I star is magnitude I squared Z, and Z is simply omega L, right? Z is omega L because that's, we're only talking about an inductor. So we have the complex power for an inductor is J magnitude I squared omega L, right? And that is against something perhaps we know. So that's the derivation. There is no reactive power. So there is no active power. It's only reactive power, which is magnitude I squared omega L or magnitude V squared on omega L, right? That's the derivation, which is quite straightforward. You can do the same thing for capacitor, which I'm not going to do because I think you can derive it yourself. You can see it's exactly the same derivation. And here, simple calculation of, if you know the voltage, you know you can determine the current. If you know the voltage, you know the impedances, you can determine the current. And once you know the current, you can find the complex number for anything you want across the entire Z and this R naught or across R naught. So you can determine. Right? If you're talking about complex power for this R naught, you need to know the voltage across it, you need to know the current through it. Yeah? If you want to know the complex power for those elements just up on the horizontal part of the circuit, you need to know the voltage across that part only and the current through that. Right? So it's like, it depends on where you want to find the complex power. So if you know which element you want to find the complex power, you find the voltage across that part only and the current flowing through that part only and do VI star. Right? Makes sense, right? You wouldn't do it any other way. If I want to know complex power for the generator, I just look at the voltage across it, I find the current through it, and I do VI star. Right? It's like I have two objects. I want to know the acceleration of the first object. I have to apply maybe force equal to mass time acceleration for that. Right? It's the same kind of thing. If I want complex power for which element? And I find the voltage and current that are associated with that element, and then we can find it. Okay? The same simple calculation here. So I won't. Yeah. Now there is some part here which I will ask Lugin to cover this part, because this part talks about reactive power compensation. Because I want to just talk to you about these three-phase circuits. Right? I want to talk to you about three-phase circuits, so that reactive power compensation Lugin will cover. I just want to talk to you about this because I won't be teaching the next couple of lectures. So I think I'd like to teach this to you before I finish today, right? The reactive power compensation. So I skipped some part, which is, you can even read it yourself, but Lugin will cover that, right? So let me talk about three-phase circuits. So we're talking about balanced three-phase circuits here, right? So with a balanced three-phase circuit, it's just three identical circuits. So think about three identical circuits, right? Think about when you think about the circuit, think about a voltage source, think about a transmission line with some impedance, think about a load. So you basically have a voltage source and some impedance and another second impedance. So the first impedance is a transmission line. Second impedance is a load. That's it. Okay? So that's the circuit. Think about three identical circuits now. Same thing. Duplicating. Right? So the first one has a voltage some magnitude, angle 0. We have three identical circuits. The generator is some voltage and angle 0. The second one is the same voltage magnitude, but instead of angle 0, you have angle minus 120. And the third, it's the same angle 0, or same magnitude, angle instead of minus 120, minus 240. Minus 240 is also equal to plus 120. It's the same thing, right? But if you don't like to think about plus 180, think about 0, minus 120, and minus 240. So the first circuit is circuit A, second circuit is circuit B, third circuit is circuit C. So the phase sequence, because we've chosen for A 0, B minus 120, C minus 240, we'll say the phase sequence is ABC. Right? ABC. All right. So in the first circuit, you have V angle 0, right? So the current, if it's an inductive load, current will be lagging the voltage, right? So the current will be I angle minus theta, because current just lags. It's just a simple circuit we have, right? Let's say the loads are inductive, right? So if it's inductive load, current has to lag. So I minus theta in the first circuit. So in the second circuit, the current will be I minus theta minus 120, because the voltage is not 0, it's minus 120. And the third circuit, voltage is not 0, it's minus 240, so the current will be theta minus 240. That's it. So that's what these equations are telling, right? So we know that if the angle is 0, the other one is minus 120, then we just shift the trig curve. If it's minus 240, we shift it minus 240, then we'll get some pattern like that. That's what we are looking at. For the currents, we'll see the same thing, because they just phase shifted. Right. So here are the three circuits, right? Here are the three circuits. And you just now connect all the three circuits together, right? You take the ground points of all three circuits and you connect them all together, right? So they're all in now one circuit. You have three identical circuits, you connect them together. So you connect the ground points, right, on either side. And if you draw a line, all current IA, IB, and IC, all collects at the node there in the Y on the right, and then they sum to 0. And there will be no current flowing on the line connecting the two neutrals, right? Because all the currents sum to 0. So you can remove that line if you like. This is no current flowing through it. Right? No current flowing through, you can remove that line. Now, how do you know that those currents all sum together? Now, remember the current was, this was some magnitude, right? It had an angle of 0, right? Or theta minus 0, right? So I angle theta you can actually factorize, because it's an exponential thing. The other one had an angle of minus 120. The other one had an angle of minus 240. So you can factorize, and you are ending up with just sum of three complex numbers. And if you sum those three complex numbers, it becomes 0. So it's 0, irrespective of what you are factoring out, right? So the sum of those three complex numbers is 0. So you have no current in the line that connects the two neutral points, right? Okay, so that's what that is. And then what is the complex power in this circuit? So it's just three identical circuits we have. Vi star would be, so we are talking about complex power in all the loads, right? So Vi star across, V across all the loads, right? Voltage across all the loads and current flowing through it, right? Vi star. We have three circuits, so it's 3 times Vi star, because you have Vi star on one, Vi star on the other, Vi star on the other, and it's 3 times that is the complex power. But yeah, so that's it, right? So that's that. Yeah. So some advantages of the 3-phase can transmit more power than a single phase situation, right? Because if it's single phase, right, you have 2 wires, right? The neutral and the live wire, right? The wire that connects the 2 grounds and the live part, and then you have 2 wires with the 3-phase. With 3 wires, you can, with an extra wire, right? Instead of 2 wires, now with 3 wires, you can transmit 3 times the power, isn't it? Because you don't have a need for that wire that connects the 2 neutral, right? So you can utilize for something. Yeah, with 3 wires, you can with an extra wire, because if you have one circuit, you have 2 wires, right? If you have single phase, right? You need to have this circuit. This circuit here, VA, voltage source VA, and all that line connecting the impedance, right? And also this line that comes back, connecting the 2 neutrals, right? Yeah, but and that will carry certain amount of power. Now instead, I remove this line because it's 3-phase. I remove this line. Now I have, instead of 2 wires, I have 3 wires, and I can carry 3 times the power. So that's an advantage, right? Torque of 3-phase machines is constant. So when the torque is constant, there is less vibrations, right? 3-phase machines use less material for the same power rating. So there are some advantages like that, right? Now, here is what you call a star connection, right? Or Y connection, because if we look at this, these generators are connected in a Y, right? Connected in a Y. Yeah, so it's a Y connection. And also the loads are connected in a Y, so it's a Y connection, right? So here we have the Y connection. We have VAN is the voltage of that generator, is some magnitude angle theta. All the generators are identical except the phase angle. So VBN is theta minus 120, VCN theta minus 240, right? Now VAB, if you know vector notation, VAB is VAN minus VBN, right? Or VAN plus VNB, right? VAB, so which turns out to be exactly VAN minus VBN is VAB. And then we can, how long you guys want to wait? I think we're up with time. Do you want to continue, or you want to? I'll leave it up to you. You want me to continue or continue? All right. So if we do that, right? Okay. I wish I have a pen to write. Yeah. Okay. Let's leave that aside because I don't have. I'll show this curve to you. Because okay, now for you to fully understand 3-phase, you need to be able to draw everything in here without having to look at it. Okay? So make sure you know how to do that. And I'm going to tell you how to do it. Right? Okay, so we have VAN. VAN is this voltage of this generator. Okay, this voltage of this generator has some magnitude and has some phase angle, and that phase angle is 0. So you have this vector here. Do you see this VAN? I'm a little bit handicapped because I can't draw it, but that's okay. I'm just still trying to explain it to you, right? So VAN is that. Remember I talked about VBN. VBN is the same thing, 120 degrees behind. So VAN, you know how to draw that arrow, right? So VBN is the same magnitude, 120 degrees behind. So you need to be able to draw that, okay? So you remember that's the circuit, right? And you know ABC is the phase sequence. So now you have drawn this vector VAN, which has angle 0. Now VBN, you know it's the same magnitude as VAN, but 120 degrees behind. So you know how to draw this vector VBN. You know how to draw that vector. And you know that VCN is 240 degrees behind VAN, or 120 degrees behind VBN. So you know how to draw this vector, VCN, right? So you know how to draw those three vectors. You don't need anything. You need a piece of paper and pen. You can draw it without looking at anything, okay? Now, let's look at this picture. You need to draw this picture as well. Drawing this picture is not hard because you have three sources, and one point in the middle is the neutral, and that line is A. One of the line is B, the other line is C. So we have VAN, we have VBN, we have VCN. So when you write VAN, VBN, VCN, you know what you are referring to in a circuit, right? You guys always refer to a circuit because then you know what you are kind of thinking about. Yeah. Otherwise, it becomes difficult. You don't know what you're thinking. Yeah. It becomes easier when you know what you. Now, so what is VAB? VAB is the potential difference between A and B, right? It's the line-to-line voltage. Yeah, because A is a point on the line, B is a point on the line, right? So it's line-to-line voltage, VAB. Potential at A with respect to B, right? VAB. Okay, what is VAB? Is VAN minus VBN, correct? VAB is VAN minus VBN, vector notation, right? Okay, so here is VAN, here is VBN. We need to subtract that, right? If that is VBN, minus VBN is the negated. You just reverse the direction, right? These are vectors. So, right? So we can shift them. So I can shift them up to that point. So VAN minus VBN is that long vector that you see with an angle of 30 degrees, right? That long vector is root 3 because it's only root 3's are involved, right? Root 3, right, with an angle of 30 degrees. So we now know VAB is root 3 times VAN, right, that magnitude of the VAN vector, and has an angle of 30 degrees. Because when you draw it, you can see there is 30 degrees there. Right? So now you know VAB. Okay? So you know how to draw that vector, VAB. Now you know the phase sequence is what? ABC. I mean, you can keep doing it the same thing for all the other triangles, but I'm going to tell you an easy way to draw the other ones. You know the phase sequence is ABC. So you have VAB and then VBC and VCA. Okay, ABC. Right? VAB, then VBC and VCA. So if you know VAB, VBC is 120 degrees behind. So here it is. VAB, VBC is 120 degrees behind. 30 plus 90 is 120, VBC. BCA is another 120 degrees behind. So you can draw those vectors as well. So in this diagram now, you have drawn all the vectors and you know the magnitudes, right? So you should be able to draw everything in that slide without having to look at it, by reasoning it out, right? Reasoning it out. Okay. What else can you tell here? We define what we call phase voltage, phase currents, line voltages, and line currents. Okay. What is phase voltage? Voltage across an element is a phase voltage. Current through an element is a phase current. So if I look at this circuit, voltage across this voltage source is a phase voltage. So VAN is a phase voltage, right? Current that is flowing through that has to be a phase current. So IA, if I say the voltage that flowing through that voltage source is IA, I'll say that is the phase current. Okay? Now, what is line voltage? Well, voltage across lines is a line voltage. So VAB is a line voltage. Line to line voltage or line voltage or line voltage, same thing. Is a line to line voltage, VAB. Now, we just derived just now, VAB is root 3 times VAN. What is VAN? VAN is a phase voltage. What is VAB? VAB is a line voltage. So the line voltage magnitude is root 3 times the phase voltage for the star connection. This is a star connection. So the phase voltage and line voltage are different for a star connection. Right? They are different. They are out by a factor of root 3. Line voltage is root 3 higher than the phase voltage. Right? Now, the current that flows through here, that IA that flows in the line, also flows in the voltage source. So, the phase current is IA, line current is also IA. It's a star connection. They are the same. They are the same. So, in a star connection, line current and the phase current are the same. So, in a star connection, the only difference is the line voltage and the phase voltage. Right? And they are out by a factor of root 3. So, everything in here, you should be able to just draw without looking. Then you know that stuff. And you must be able to see the phase current and the line current are the same for star. Phase voltage and line voltage are different for a star connection. Line voltage is higher for a star connection than phase, and it's out by a factor of root 3. Right? You must be able to see that. So I've told you how to draw, how to reason out and draw this by yourself. Okay? Now let's look at the delta connection. Right? Okay. Now again, with this delta connection, you need to be able to, because you can derive all that once you know that. Right? You can derive all those formulas, everything makes sense once you know this also, for delta connection. So for delta connection, again, you need to be able to draw everything in here without having to look at it. Okay? So how do we reason out and do this? Right? So let's think about that. Let's think about how to do this. Okay, so we have 3 lines, A, B, C. I think you can remember that. Okay. And then there is this delta connection means a triangle, right? I think you can remember that as well. Okay. So And in the delta, there are 3 circles. I guess you can remember that as well, right? So you have these 3 circles. Now, this point here is point A. This point here is point B. So we can mark voltage AB, right? VAB. I mean, that's the, you wouldn't say any other way, right? VAB. And the phase sequence, what is the phase sequence? ABC. So if I remember I have to put a VAB, then I need to put VBC, and I need to put VCA. We wouldn't do it any other way for phase sequence ABC, right? So we have VAB, VBC, so positive is there, negative is there, and VCA, right? And for currents, we'll have IAB, VAB we had, so IAB we must have, and you must remember IAB means current is flowing from B to A. There are a few things you need to remember, right? So current flows from A to B, IAB means current flows from A to B. Well, if you have IAB, obviously you will have IBC, and you will also have ICA, right? Because ABC is the phase sequence. So you can see IAB, ICA, and IBC. IBC means current is flowing from B to C. Okay, you will know that. Yeah. Now, so we have drawn this diagram, right? So you have to know. I gave you some reasoning to draw that. You have drawn that. Now we need to draw this. Now remember when we did the star connection, VAN was our reference, right? VAN was our reference vector. In this situation, in the delta connection, our reference vector is going to be IAB. VAN was our reference vector for star connection, right? IAB will be our reference vector for delta. Because reference, you can choose anything for your reference. You can choose a voltage, you can choose a current, you can choose anything. Yeah? So IAB we choose as a reference. So IB, because everything is out by 120, IAB, so IBC has to be 120 behind that. ICA would be another 120 behind that, right? So we have IAB, IBC, ICA, 120 degrees apart. You can do that. You can draw that, right? And then you look at this current IA. What is IA? IA is IAB minus ICA, right? We can see it from this diagram. This is IAB minus ICA, right? CA is that, right? Minus ICA means I need to think about this vector going down here. I can then move it up to that point and then add these two, right? And then I get this vector here, which is IA. And it's bigger than the little vectors we are subtracting or adding after negating, right? So you can see here the line, just like the line voltage was √3 higher than the phase voltages in star connection. In the delta connection, the line current is actually √3 times bigger than the phase currents. Because what are IAB, ICA, and IBC? They are all flowing through, or they are currents flowing through the generators. So they are phase currents. Yeah? And what are flowing through the line? IA is the current that is flowing through the line, and line current is different to the phase currents in the delta connection. But in the star connections, they were the same. But delta connections, the currents, line currents and the phase currents are different. Just like in the star connection, the line voltage was √3 times bigger than the phase voltage. Here, line current is √3 times bigger than the phase currents. in the delta, right, is bigger. But look at the phase voltage and the line voltage. Phase voltage is VAB, is a phase voltage. What is the line voltage is the same, VAB. So in the delta, the phase voltage and line voltage is the same. Right? Is that correct? Yeah? Right. So I think that's pretty important. And once you get that, once you can draw these two pages, all the pages will make sense to you. Don't even have to explain after that. Right? So you can see the in a star connection, one of the quantities, right, or delta, one of the quantities, the line voltage or phase voltage will be out by a root 3. Okay? So now think about complex power, think about apparent power. V phi times I phi, 3 times V phi times I phi is the complex power, apparent power, right? 3 times V phi times I phi, yeah, apparent power. Now, if you're talking about star or delta, if you're talking, that's phase quantities, but if you're putting line quantities, instead of V phi and I phi, if I change it to VL and IL, it doesn't matter whether they are star or delta, one will be out by a factor of root 3, so that 3 we can convert to root 3. Root 3 times VL IL will be the same as 3 times V phi I phi. Because it's only one of those things will be root 3 higher. So that 3 becomes root 3, gets multiplied by the root 3 already built into the line thing to become 3. Right? Yeah? Okay. Yeah. Yeah, I mean, that's the convention that we have to adopt a convention, right? We've chosen the convention IAB means current flows from B to A. But if you use a different convention, you will come up with the same answers. But you have to be consistent. Because we said IAB, current flows from B to A. ICA, current flows from point A to point C. It's like when I say F equals MA, I can say upwards is positive, or I can say downwards is positive. Doesn't matter. As long as you are consistent throughout your whole calculation, everything is fine. Right? So when you say IAB, I'm saying it goes from B to A. Correct. But if you're not happy with that, you can change your convention, but you have to be consistent and you can see if it makes sense. But here it makes sense, everything. Like I've shown the circles, right? Everything makes sense. But you have to adopt one convention. And the convention that we are using, positive P, positive Q means it's a consumption. A negative will imply a generation. So I think we've gone a full lecture and a little bit more. I would like to teach more, but I think Lu Jin will take over and I will see you sometime later. All right? Okay.
Depends on.
It'd still be the same regardless.
Yeah, you have a pen?
Yeah, pen, yes.
Yeah, thank you. So the way I would think of it is like this, right? So let's say I have admittance. See, I have something.
Yeah.
Right? It's point A, point B, right?
Yep.
So this is R and this is X,
Yep.
right? JX, right? So impedance AB is R plus JX, right?
Yeah.
Let's say this is R1 theta, okay, theta 1,
Yeah.
right? So if I now want to do YAB, is 1 on ZAB,
Yeah.
which is 1 on R plus JX, right?
Yeah.
Which is also equal to 1 on R1 theta 1, right?
Yeah.
So this thing here, this is angle 0, right?
Yeah. That's angle 0.
So then it's 1 on R1, angle minus theta 1.
Yeah.
Yeah? So what, I'm pretty sure this is correct.
Yeah. No, that is correct. Yeah.
Yeah, that's the way.
Oh,
it is.
but
Yeah.
oh, because what I'm interpreting it is that the way I interpreted it was that y equals
But I think we are talking then two different things here.
g plus and then j
Yes.
b, which would be 1 over r, and then
Yeah, but
well,
we are,
this would be minus
yeah,
j over
X is it?
x.
Yeah. But see here,
That's a
so here we are talking about this circuit. You're talking about a different circuit. You're talking about this circuit.
Okay.
It's the same element, but you're talking different circuit.
Yeah.
Because for you to be able to do that, do this, you're talking that.
Okay, now that makes sense then.
It makes sense?
Yep. Cool.
See, so this is YAB for that. Y for that would be is what you got.
Yeah. Okay. Cheers.
Yeah.
Yeah.
Thank
makes
you.
sense. Thank you.
Thank you.
I had a quick question. I get that picture, but in this one, I was a bit confused on what the said.
Okay. So here, because we want to know how all the voltages, how the currents and everything moves, what it is. We do it.
Does this make the previous one? Does it make sense?
Oh yeah, same issue.
Same issue.
Yeah.
Okay. Should we look at this then?
Yeah.
Okay. So we know that okay, we have these identical sources, right? And if we take VAN as our reference, then we know VBN is 120 degrees behind, one CN is 120 degrees, another 120 degrees behind. So behind. So why are we doing that? Because we want to have an understanding. If we knew one of these, then how they are linked to all the other voltages.
If you know one, you can find the rest.
Yeah, you can find the rest. Right? So then if I say, okay, that's my reference, then once I know that, I know that. Yeah? And then once I know those, right, these are just voltages across here and here and here, right? Then I want to know what that is. Voltage across A and B.
Let's say line voltage.
Line voltage. Yeah? I want to know what is line voltage. Then line voltage, VAB is VAN minus VBN. Right? So if I want to add two vectors, I have to negate VBN first. I have VBN. Right? Because VAN minus VBN, right? So I can add two vectors if I negate this. I can add that and the negative as well.
Alright.
So I negate that. Becomes that. And I want to add the negated one, then I shift it there.
Alright. This one is it's pretty much like half based off that
Yeah.
diagram.
Yeah.
Yeah, that makes sense.
Okay?
Yeah.
And the other one is the same.
Same concept.
Same concept.
Yeah.
Okay. Yeah? Okay.
Few questions. First, like when we at mock cases, it will be like more